All right, though. So, two things up first here. We've got, I know we've been dry for a lab for a little while here, but we've got two of them coming up with our Chapter 13 stuff. So, those are up posted now. If you want to get an early start on those things, you are more than welcome to. I'll talk about those a little bit more when we actually get diving into them and everything else, a little bit more detail next time around. But it is up there if you wanted to get a head start on those things and get them out of the way early. You'll have some time to do those anyway, so no rush on those. But today's our last day with Chapter 12 here, right? Or at least our last day of talking about it in lecture like this. We are finally closing out. We are putting in the last piece. You can already see down here, we've kind of got what's it going to look like when we've got all of the pieces in here together. So let's go ahead and jump right on into it. Now, this is something that I've talked about just a little bit already. But when we're talking about kinematics of like real objects, specifically rolling objects, acceleration is wonky. It's not quite as easy because, see, not only are we putting energy into the translational kinetic energy, but we also have to put energy into the rotational kinetic energy. And we've seen how to do that now. We talked about that last time. But this strange feature means that the acceleration is like not quite what you would expect it to be, right? There's a little bit of other stuff going on here that's messing up that acceleration, that's stopping it from just being our g sine of theta that we'd expect down the slope. The fact that torque has to be applied, the fact that energy has to go into this rolling motion, stuff like that means that it's not quite as simple as we would normally like it to be. But that's all right, because we don't need kinematics for this stuff anymore. We know how to use energy for these things. So I just wanted to bring this one up one more time as we're talking about these things, when we're talking about them in terms of like non-slipping or anything else like that. Keep that in mind, that this is specifically when the rolling is not slipping. If there's no friction or anything else, it can't roll, right? Remember how that rolling motion actually works. The part that's on the surface is sticking there. If it's slipping, if your tires are spinning in place, then you're not actually going anywhere, right? You're just like, it's the phrase, you're just spinning your wheels. Right? You're not actually going anywhere because you don't have any sort of traction. Your wheels at that point are slipping. It's only when they're not slipping that we actually get this rolling motion. So keep that in mind. That's a little bit of a hint for a question you guys are working on. But I want to dive into one of these things. Let's take an older problem, one that we have seen before, and let's recontextualize it just a little bit. Right? You might have made some sort of marble roller coaster or something like that before in your life. Right? I think these are quite enjoyable things to make. I have seen some very elaborate ones. I have built some very elaborate ones. They don't need to be good to be elaborate. I want to emphasize that just in case anyone's like, mine was piddly. No. They don't need to be good. It's better if they're not, actually. But let's imagine here. We've got something going on like this. We've got a marble, sits at the very top of this hill. It goes down into this loop-de-loop. Right, and in this one I've chosen loop the loop because it's the other way to write it and it's disgusting and it bothers me, but we've left it in anyways. It's got a radius r. The marble has a radius lowercase r and a mass m. You'll need both of those. Find an expression. What height do we have to be to make sure that it goes all the way around the loop? You have done this before with forces. And, well, specifically at the time, energy conservation and forces. Now we're doing it with energy conservation and forces, but also rotational energy gets involved as well. So I'm going to say take the first 5 minutes or so here. Let's see if we can come up with a good expression for what this thing should look like, and then we're going to come back together and see what you got. All right, so I want to start to take a look at this one, and I've got to be honest, this one's perhaps a little bit deceptively difficult. But let's get into that. Right, let's figure out, what do I mean when I'm talking about deceptive difficulty here? What else is going on that we might be missing in a problem like this? We're going to just erase those couple words that we've got up top here. Oh, whoops, didn't start a new one of these. It's all right. Paste this thing in, move it over. Let's see what we've got. So I don't need to blow this thing up too much because I think I'm going to draw kind of separately from this thing anyways. Because realistically, as we're looking at this thing, let's talk about it like this. Do I really care about anything that happens right here? Does that matter to me? We don't really care about anything that goes on here. I would argue we don't really care about anything that goes on down here at the bottom either. right? None of that stuff actually matters to me that much because, well, frankly speaking, I'm much more focused on which part specifically. What's the most important part of this thing? From the very beginning, we're at the very top. That's one important part. What's the second most important part? Yeah, when we're at the top of the loop. So we need to think about that. Okay, at the very top of the loop, let's draw it out like this. I'm going to draw this thing really big to start, and then we'll do that same kind of deal where we kind of erase the parts that we don't need. So let's draw this thing really big, just like this. Let me get rid of all of the extra stuff. We don't really care about the rest of the loop. We really only care about the very, very top of the loop. And then, of course, we have our marble that's, try and steal this color. Something like that. Bam. Most of this explanation because your internet's died? Not to worry. My computer died. So you haven't actually missed anything. Oh, good. I love when it does this. All right, we'll just manually color this thing in. There we go. There's our marble. And the reason that I'm doing this is because I actually want to see what's going on with this thing. I want a good view of this. So, all right. I've got a couple concerns here, but let's talk about these pieces first. Let's first think about our free body diagram. Let's not go too crazy quite yet. So I know that I would have my radial direction, right? I'm focused on that radial direction. What forces might I see here? I'm thinking of two in particular. Gravity, I agree with that. Maybe a normal force. Who's to say? We'll find out, right? So I would agree. Gravity, though, that is certainly going to be there because we're not getting rid of it. And then maybe a normal force, right? Question mark? Normal force? Now, our minimum height would indeed be when the normal force is equal to 0. That's the big important deal here. So if we're a little bit higher than that, right, ideally when you're setting up some sort of roller coaster, you are not at a strict minimum of, oh no, we might fall off the loop, right? That's not a very good thing when you're talking to your insurance company or anything else like that. I'm thinking specifically roller coasters here. With marbles, of course, it's not that big of a deal unless your marbles have lives, feelings, and personalities, which, unless you are Gel's Marble Runs, I don't expect they do. Which is a fantastic channel. He does professional marble races, by the way. Absolutely fantastic. But anyways, we know the net force in the radial direction must be the centripetal force. Must be the centripetal force because we're moving in a circle. If we're supposed to be still moving in a circle, then we need that centripetal force. Now, the minimum is when that normal force starts to go to 0. Right? As we get slower and slower and slower, the normal force is doing less and less and less until it goes to 0 right at the very top. And if it goes to 0 anywhere before that, we fall. So that's our big sticking condition. If the normal force is equal to 0 or very nearly 0 right at this point. So that's our spot of interest. Now, we've got some strange details. And let's talk about some of those strange details here. First, let's go ahead and write out this expression that we just said. We said, okay, well, the net force in the radial direction must be equal to the centripetal force. We said, all right, well, that's probably going to be coming from gravity and perhaps a normal force, but we know that this normal force is going to 0. That's our limit here. That's our minimum height. Normal force has gone to 0. What is my centripetal force here? More specifically here, what is my radius? Which radius do I use? R's on the right track, but it's not exactly the circle that we're looking at. See, this is the nasty bit, because when we're talking about motion like this, moving around in the circle, we're still focused on our block or our particle or whatever. The situation here is a little bit more difficult because what we're actually looking at is that the circle that we're moving in is not actually this black line that I've drawn. It's this line right here. This is something that, admittedly, we kind of neglected when we were talking about roller coasters. because for the most part, we assumed a few different things. For one, that it was much, much larger than this thing to worry about anyways, but looking at this chart right here, it's a pretty comparable size. I would think that we have to actually worry about it, and now we actually do know some dimensions about our shape, right? And that's the big sticking difference. Is the last time when we were talking about these things, blocks going around a loop or anything else like that, we had no idea the dimensions of the box or anything, right? There was no way to tell where the center of mass was. We hadn't had that discussion yet. So, the name of the game, and one of the kind of favorite quotes from an old professor of mine was, every year we lie to you just a little bit less. And that really goes on a week-by-week basis. Every week we lie to you just a little bit less. So now, Band-Aid's off. At least this lie has been revealed. Now we're actually treating this thing how it should be treated. And also, maybe you'll appreciate why we did lie to you. But anyways, so we go ahead and plug that in, right? The actual radius of the circle that we're going around in is not capital R, but it's capital R minus the radius of the ball itself. So let's go ahead and write that in. V squared over R minus R. Okay, so now we've got that. And this condition, right, this is basically saying to us that we need to have some sort of velocity equal to G capital R minus R, square root of that. That's the speed that we need to be at the top of the loop to make this happen. So now we ask, where does that velocity come from? Why, of course, it comes from gravitational potential. So let's go ahead and do that. Let's go ahead and say, all right, well, at the very beginning here, we start with all of this potential energy. And how high are we up? Where's our center of mass? The center of mass is at mgh plus r. A cruel fate indeed. But that's all right. We can work with it. It's not too bad. It's just a little bit of an extra term. We've got some more parentheses to throw around, but that's okay. So now we know that this thing is going to go into, for one, translational kinetic energy. Right? And I want to stick with my translational kinetic energy because this is the description we've been using for quite some time, and this is a description that works very well. Technically speaking, we could go into the rotational kinetic energy around the circle and then the rotational kinetic energy of the marble itself, but that sounds like a lot more work than it's worth, if I'm being completely honest, because then I got to keep track of 2 omegas and yikes. What I would rather do is I would much rather just say, all right, well, that's going to be split up into a 1/2 mv squared, ding, ding, ding. But also, what makes this a little bit more difficult is that this is also going to be a 1/2 I omega squared, and this is the rotational kinetic energy of the marble itself. This is the marble spinning in place, right? That's the energy associated with that. So, we are dealing with a marble, though, and generally speaking, marbles, they've got a pretty specific shape, right? I know almost every marble I know is in a sphere. So because of that, I can immediately say, well, that the moment of inertia should be 2/5 mr squared. Good start so far. We also know that based on this rolling condition that we've got, that this omega right here, omega is actually v divided by r. Perfect. So now I've got a good thing going for us here. Let's go ahead and plug some of these values in that we've got. For now, I'm going to leave v in place just to see if we can simplify this a little bit first, but I do know that I'm ready to plug this in as soon as I'm there and ready. But let's go ahead and say 1/2 times, here's the moment of inertia, 2/5 mr squared. And then, of course, my velocity, or my angular velocity, rather, is going to turn into v squared over r squared. Okay? So my r squareds are going to cancel out, and what I'm going to be left with here is 1/2 mv squared plus 1/10 mv, no, 1/5, geez, 1/5 mv squared. That sums up to be in total 7/10 mv squared. So here we are. Now, this is going to get a little bit nasty. right? Now I'm going to go ahead and plug in what I've got for V. So here's what this is going to turn into. I'm going to get rid of these. Do we have to have the moment of inertia table memorized? Absolutely not. We don't memorize a ton of things in here. Conceptually, we do want to talk about things and have a good understanding of what's going on with those, but like quantities themselves, no. I've got a question for everyone. Have I been on my game this entire time? Is this complete? What do we think? Is something wrong? Is there a disturbance in the force? We are missing gravitational potential, and we're not missing this gravitational potential. Of course, it's right there. We're missing it over here because we're not at the bottom of the loop. And even if we were, our center of mass is still technically a little bit off the ground. So you have to be careful with these things. This is one of those situations where I want to make sure that I've considered everything that I could possibly need on this one. I am missing one of the terms. This looks very nice and easy, right? All things considered. This doesn't look so bad, but I am missing this additional term. So what should that look like? Well, what distance are we actually at? We are at 2r up minus this radius right here, right? That radius right there. That is where our center of mass is below 2r. So I'm going to say I should also have this additional term right here, mg2r minus r. Okay. So let's keep going with this. If this were to carry down, I don't do anything with it here, right? This is still just kind of floating along, doing its own thing. No big deal, no big deal, no big deal. Then here, this is where I'm going to have this additional g times 2r minus r. Whoops, mg. Haven't canceled out the m's quite yet. Now I've got 7/10 mv squared. V squared, just kidding, V squared because we've canceled out the m's, plus G2R minus R. Okay, I'm solving out for H. That's the thing that I'm really here for. Let me take one more step of simplifying before I actually plug in what's going on with V. Let me divide everything by G. Let me subtract R from this. So what's that going to turn into? Well, I'm going to have H on one side is equal. I don't need to do too much with this. This is just going to be 7/10 V squared over G. Now on this side, this is where I'm going to tack on that R. Let me go ahead and say, well, let me subtract the R, then this can come in right here. That is, this will become, whoops, I wanted to have a 2 on the outside, R minus R. All right, we're almost there. We're getting close at this point. Now what I'm going to do is I'm going to go ahead and plug in for V squared. I know the V squared is equal to G, R minus R. G, capital R minus lowercase r divided by G. The G's will cancel out, plus 2 times R minus R. So the G's are going to cancel out. Then I've got 7/10 R minus R plus 2, or 20/10 R minus R. H needs to be 27/10 R minus R, or better yet, 2.7 R minus R. So are we having fun yet? This beautiful kind of a disaster of a question. But maybe you guys can appreciate now why we talked about specifically blocks on frictionless surfaces, and we didn't talk about where the center of mass was and all the things like that, right? All of these important details that we kind of just brushed right on over when we were talking about it the first time because we were just like, I don't want to deal with any of that stuff. Right? It's just not worth it. It's not worth it when we can get through the problem conceptually much easier without considering all of these extra details. But to be more accurate, it does require these extra details. But at this point, your guys are familiar with the underlying concepts, and that's the most important part, right? Because if you're familiar with the underlying concepts, then realistically, I know this algebra looks a little bit nasty, but conceptually, the three pieces here, we just have to be watching out for each term as it goes in each of these places. And if we can keep track of those, if we can do the setup, then the rest of it's just bookkeeping at that point. It's going through the algebra, and that's not nothing, but it's not the bulk of the work anymore, right? The most difficult part is getting this thing set up in the first place, and conceptually, that's where all that comes from. So, let's keep having some fun with it. Let's look at something a little different here. Of course, you could have seen this coming. We talked about angular kinematics. We talked about angular forces, torque. We talked about angular energy. And now, finally, to close it all out, to complete our picture of rotational motion is angular momentum. Anytime, we know that if we have kinetic energy, we probably also have some sort of momentum associated with that. So, it follows then that if we have rotational kinetic energy, then we would have rotational momentum to go along with that. Now, there's a couple different ways that we can define angular momentum, and both of these are pretty important. Right? I want you to keep this in mind as we're talking about these things. One of the ways is this quantity L right up here. Draw pad? Are you with me? Come on. Oh, there we go. A second late. This quantity right here. So first, we use capital L to indicate angular momentum. You know, for the L in angular momentum, right there, I'm assuming. It's silent and invisible. But anyways, as we're talking about this, right, this is for a point mass moving relative to some radius. So if anybody was visiting around here at the beginning, when we were talking about problem 12.90, a blob of glue smacks into the bottom of a thin rod spinning around an axis. This expression for angular momentum would work fantastic for that, because this would transform a linear momentum, P, into an angular momentum. Very wonderful, very easy to use, assuming that something goes on where you're converting linear into rotational. Now, the other way to do this is, let's say you've already got some sort of shape or anything else like that. You know the moment of inertia, you know it's spinning around. This expression looks a little bit more like what's going on with our translational momentum, because of course, we've got our mass equivalent and our velocity equivalent. Mass, velocity, momentum, angular mass, moment of inertia, angular velocity, momentum. So, between these two things, though, we've got a small variety of tools going on here to help us figure out what these things are going to be. Now, of course, right, I feel like I don't even necessarily need to go through all of these details, because as we're looking at these things, right, I think it follows pretty well that if translational momentum was conserved in collisions, then so too should rotational momentum be conserved in collisions. Right, here's a little bit more of a rigorous proof of that. If we're actually looking at the rate of change of angular momentum, the net torque, all of that good stuff coming from any sort of force, net force specifically acting on an object, and the radius that it's acting on, torque net, 0, L's constant, finals equal to initial. But the conceptually important part here is that momentum should still be conserved. Nothing has changed about that, right? As long as you don't have a torque acting for some amount of time. That was our big sticking condition for momentum as well. Remember that when we said that if we're looking at a force acting over some time, then we've got an impulse, then we've got a change of momentum. So if there's a torque acting for some time, then there is an angular impulse, there's a change of angular momentum. If there is not a torque, if there is a collision, an instantaneous kind of snapping, then momentum should be conserved. Conceptually, you know this one already. Don't be psyched out just because it's rotational now. Remember, everything that you've learned about momentum still applies here. In summary, here's what we've got. We have a full picture. Translational motion all on the left-hand side. Angular motion, all on the right-hand side. We have gone through, think about this, pat yourselves on the back. We have gone through all of these equations in these last 4 lectures. Got a new variety of things to use, but the reason that we're covering this so quickly is because, again, conceptually, nothing has changed. The variables that we see in place are not so different. There's a lot of things going on here. I know it looks different. I know I is not the same thing as M, but conceptually, they work exactly the same way. So, and I really like this slide because it kind of really demonstrates that this is parallel sets of equations. That's what's going on here. So, I want to try this out. Let's imagine a 2 kilogram, 20 centimeter diameter turntable rotates at 100 RPM on frictionless bearings. That is to say, it is essentially a perpetual motion machine. We make it spin and it never stops spinning. 2 blocks, 500 grams each or 0.5 kilograms each, fall from above, hit the turntable simultaneously at opposite ends of the diameter, and stick. We've got some Gorilla Glue on the bottom of each of these things, and they instantly stick, and it's super fast drying Gorilla Glue, so it dries instantaneously. And that's also to make sure that it doesn't just kind of flip over to the side, right? Balanced forces, all that good stuff. What is the turntable's angular velocity in RPM after both blocks have hit? Obviously sold in the classical physics shop, yes. Frictionless bearings. Well, no, I said we've got an issue with perpetual motion. Well, this is maybe the stuff that they've got in the back that is not strictly legal. We'll go with that. But anyways, take what we have just seen with some of these details, right? What's going on with something like a point mass or a block? What the angular momentum coming from that block might be? And then think about what goes on with the conservation of angular momentum after the fact. Take the next 5 minutes or so, and then we'll take a look at it together. All right, so let's go ahead and start taking a look here. So here's where I'm going to be a little bit cheeky about it. You know how I love to not write down my variables. You know how I love to solve these things exclusively with symbols and only plug in numbers when it's very, very, very convenient. I'm going to do it again. Watch me do it. Let me start by drawing a picture, and I'll talk about the variables that we're given, but we'll deal with it in a little bit. We know, technically speaking, I've got a turntable that has, let's see these details here, 20 centimeter diameter turntable. So that is a flat disc that has a certain mass to it, all that good stuff. So let me go ahead and say that my mass, 2 kilograms. That's big M, my little mass. Each of these blocks is going to be 0.5 kilograms. I know that the diameter, I keep forgetting this already, 20 centimeter diameter, which means 10 centimeter radius, because I hate diameter. And then finally, the last thing that we need here is that omega is 100 RPM. And let's call this omega initial, because this is before the blocks are dropped on it. We're going to say, all right, well, then we're going to find omega final after this collision. So let's talk about these 2 separate pieces. Initially, I have some sort of disk like this spinning around in place, right? Fantastic, wonderful, but whatever, right? Or maybe let's go ahead and do it like this. Let's go ahead and draw our 2 blocks. We'll make these green this time around. Let's have those be on the side, something else like that. They're not on quite yet. How much momentum do each of these blocks have? What do we think? None. Rotational or translational? Hey, I'm being cheeky with it. It's both, right? If it doesn't have, if we go back to that expression that we had from before, angular momentum, look at it like this. Angular momentum, capital L, is equal to R cross P. This is true for an object that was already moving in a line. If it was suddenly converted into rotational, then this would be the expression. So if regular momentum was 0, so too would angular momentum be 0. Not to worry. Okay. So then each of those things is contributing nothing. I know that the disk is spinning around at, let's go ahead and say like that, at some initial omega, right? All that good stuff. So let's talk about our initial versus final momentum. We'll do a little arrow to say we're going over there. We're going to say, all right, well, we start with, well, probably the easiest way to do this is just I times omega naught. And of course, when I'm talking about I omega naught, what is the moment of inertia of a disk spinning around just like this? Well, you don't have to have it memorized. Again, of course, I don't expect you to, but it is probably a good thing to have that table handy. So anytime we're looking at it like something like that, a disk is always going to be, oh shoot, I want to make sure that I'm not actually just goofing this up. Should be a 1/2 mr squared. Well, I want to make sure before I say something really dumb on that one. I had this here, and then I didn't write it down. Fool that I am. That's all right. Have this table handy somewhere. We should have it somewhere in the files for the course as well. So if we're looking at all of these things, not even in this one. Here, there we are. Where's our flat disk? 1/2 mr squared, cylinder or disk. So this will be 1/2. I said this will be this. There we go. This will be 1/2 capital M r squared omega naught. Perfect. That's it. Now we look at the second state. Now these two blocks have collided. They are now sitting on top of my disk. And my disk is no longer spinning at the same rate as it was before. So let's imagine the blocks look something like that. Each one is there taking up a little bit of space. They fall right on the edge or as close to as possible without falling. That is to say, the center of mass is r away from the center axle. Right? We know what turntables look like. All that good stuff. Center axle right there. So then, there's a couple different ways that I can imagine this, but probably the easiest way is to just immediately think, okay, well, great, I omega. No different, right? That's the exact same thing. I would expect it to be. But let's call it an I final. Omega final. That works for me. I'd be happy with that. But we need to talk about what is our shape now, because our moment of inertia is no longer 1/2 mr squared. Now, as we would see for this object right here, what we would rather say is that I final would be the moment of inertia of the disk. That's still there. But now we have two individual point masses adding on to that. So, of course, I'm following my mr squared kind of thing, and I sum up every single moment of inertia, right? That is the wonderful thing about these. Even if I have a continuous shape and point masses, whatever combination of objects I have, if I'm looking for the total moment of inertia, I just need to sum up the individual pieces. So that is 1/2 mr squared, capital M, r squared. One block, mr squared. Two blocks, mr squared. Bam. Nice and easy. So we come down here. This is going to become essentially 1/2 capital M r squared plus 2 small m r squared omega final. Now, my whole thing here about not converting into radians per second, right? I made a big stink of that right at the beginning here. Why don't I have to worry about converting into radians per second? Why did I leave this in RPM? Am I just lazy? Well, I mean, that's part of it, but why can I get away with that? Yeah, my answer is also in RPM. I'm not using any sort of transformation equation. It's not MA is equal to F or anything else like that. This is I omega is equal to I omega. So if omega is RPM on one side, then omega can be RPM on the other side, and that's totally fine. I'm using RPM to find RPM, right? I can't plug in RPM and expect to get radians per second out, though. That's the big key trick here. Keep track of those units. So let's go ahead and do that. Let me just say, all right, well then, as we're solving out the rest of this thing, I would, kind of rather not do anything else with this. I know it can be simplified just a little bit on this one, but, well, we can get rid of the r squareds. Let's get rid of the r squareds. That'll make this a little bit easier at least. Then this is going to become 1/2 capital M omega naught divided by 1/2 capital M plus 2 lowercase m is equal to omega F. Plug in all of our numbers here, and what we should actually find is something like 50 RPM. Are the two smaller masses considered point masses? Yes, more or less. Without any sort of specification of their dimensions or anything else, this is going to be kind of like a play-it-by-ear kind of circumstance. If I look at this thing and I say, okay, diameter, turntable, continuous shape. Sure, I know that that thing's a big disc. 2 500-kilogram blocks. Blocks is immediately, without any idea of what these things are, dropped from above, hit the turntable simultaneously at opposite ends of the diameter, and stick. Without any more information here or anything else like that, if they had said that the block has this dimensions, X, Y, and Z, and it falls so that the outside edge lines up with the disc, then I might need to be a little bit more careful. But of course, by then, we have a more complicated problem on our hands. So with the details that I've got right here, they tell me that it's just blocks. I say blocks, point masses. I don't know the difference. Falls right on the outside edge. And yes, that is our 2mr squared, because each block is an mr squared, right? That's the 1 block, 2 block. Let's try a wonky one here. This is a really fun one. I love this one. Pencil has mass capital M, length capital L. It is standing up on a table on its eraser end, right? Balancing things as we might want to in class. A slight push, very, very slight, no real impact other than allowing it to tip, causes the pencil to fall over, and friction between the eraser and table provides a pivot point. Right? And you can try this one out yourself if you would like. I'm trying to see, do I have a regular pencil? I don't have a regular pencil. I only have like pens everywhere. But anyways, you can try this one out yourself real fast, see what happens, right? For the most part, for the beginning of that, it's going to tip according to that eraser, because of course, the eraser made of some rubber polymer kind of thing right there is actually going to stick pretty well to the table. Find an expression for the speed of the tip of the pencil as it hits the table. So what concepts do you think we have to use here? Let's talk about that before we dive in all the way. What concepts are we expected to use? Do we expect to see conservation of angular momentum? I don't know if I'd agree with that. There's a constant force acting on this thing, right? If it was given a slight tip, there's a torque now acting on it because of gravity. A torque exerted for some amount of time will change our angular momentum. Conservation of angular momentum is not a good way to go with this one. There's no collision. If there's a collision, then conservation of angular momentum is a lot better to use. But in this case, no collision. So I'm going to say energy might be a better way to go. That's what I would probably recommend. But go ahead and work on this. I want you to work on this for the next, say, 5 or 6 minutes. Because I know it's a little bit difficult. It's a little bit strange. But think about what goes on. Think about where the energy is at, where the energy ends. Consider all those details together. And then we'll talk about it in just a little bit here. Okay, I want to start to take a look at this one. So here's what I'm thinking. What kind of energy are we going to end up with here? Tell me about all the forms of energy we might have at the end. Kinetic, but be a little bit more specific than that. I think I'd agree rotational. Why not translational? What's our big sticking condition? How would we know if this was going to be translational rather than just rotational? What would we expect to see? Imagine a scenario. What's some sort of, yeah, some sort of slip. Then I would imagine that I'd be seeing some sort of translational kinetic energy. If the pivot point was moving, then I would agree that there would also be a translational kinetic energy. But because the pivot point, as we're told, this thing sticks, and let's say this has never existed, but a perfectly round eraser on the end of a pencil. First of all, there's no way, right? It's never happened before. But even if we imagine that it could, as this thing starts to fall down, the pivot point stays in the exact same place the entire time. If it starts to slip, if the entire thing starts to slide, if that pivot point is moving, then I would argue that there's translational kinetic energy as well. But right here, because we're told that it just essentially sticks at that point, falls all the way down, I would much more expect that this thing right here is going to be exclusively rotational kinetic energy. And because of that, this is going to make this whole problem significantly easier to tackle. Let's go ahead and copy this thing over first. Steal a picture of this thing so we can use it. Something else like that. We probably don't need all those details, but I might just leave them on because it's more work than it's worth. Let's take this thing up here. All right. So with this in mind, we're going to try and draw this thing out. Let me go ahead and do a very poor job. I'll do it in orange so that we can actually see it. But here's our pencil. The tip of the pencil probably looks something like this. Let's assume the entire thing is graphite. Looks a little bit more like a rocket at this point, but that's all right. Steal this color right here. This is our eraser at the end of it that has been... Oh, yeah, that's a good picture. Oh, boy. What? Oh, what? I hate it. We're not going to do that. All right. Close enough. So let's go ahead and do this, though. Let's go ahead and label. Here is our pivot point. I want to mark it like this so that I keep track of, hey, pivot point right here. While I'm at it, I'm also going to mark this spot right here. See, this is my center of mass. This is my center of mass. See what's happened? Pivot point has not changed, or very small change. Center of mass has. All of our energy when we started, then, assuming that we started with no rotational, and I said no, just a really, really, really tiny push. No rotational means that we started with exclusively a lot of potential energy. Specifically here, mg, or I guess we're using capital M, fine, capital M, g, L over 2. That's our height. If this whole thing is L tall, then our center of mass right now when we start is L over 2. It ends at 0, or just about. All of this goes into rotational kinetic energy. That is 1/2 I omega squared. Why are we interested in omega? What does that actually relate? What are we actually trying to find here? Remind me, I'm off the slide at this point. What am I actually looking for? So the value that we're looking for is specifically thin rod about the end. That's about what we've got right here, 1/3 ml squared. We will need that here. But we're looking for the speed of the tip of the pencil. We're looking for this speed right here. And that means that if we find omega, omega is my rotational velocity, then I can convert that into a translational velocity of the tip specifically. So if we find omega, we've got VF. So let's find omega then. We just saw from that table right there that the moment of inertia of, well, a pencil, any sort of thin rod like this where the pivot point is the very end, I is equal to 1/3 ml squared. With that in mind, we go to plug that in down here. We would say, okay, this is capital MGL divided by 2 This is 1/2 times 1/3 ml squared times omega squared. Okay, so this is, I might as well just cancel out these 1/2s. That seems to me like a reasonable thing to do. Cancel out the 1/2s, then I'm left with a 1/3. I'll cancel out the capital M's. We don't need those. And I'll cancel out one of these L's. We don't need all of those. And I know I have just gone kind of through like a crime spree of things that I've done to these variables, but let's look at what we've got left. L over 3, G is equal to L over 3 omega squared. Good so far. And let's pause right there. Let's go ahead and replace omega with what we're looking for. Remember here, I probably actually jumped the gun on this even. Omega times the radius is equal to V. What is my radius here? L over 2, 3L. What do we think? I wouldn't say L over 2 because my radius from the center of mass, L over 2, I would agree with that. But we are not spinning around our center of mass. We're spinning around this pivot point here. So our distance is the full L out to the tip. That's the circle. That's the circle that actually is spinning in place here. So replace this, not R, L. So I've jumped the gun a little bit. I probably should have left that L squared there, but that's not a big deal. That is to say, omega is equal to V divided by L. So when we do that replacement, we get G is equal to, one of the L's is going to cancel out. I'm going to have V squared over 3L. V is equal to square root of 3GL. And there we have it. So, as we dive into this stuff, I've got one last one for you here. And here's where we get very nasty. Let me just rip off a few of these band-aids, a few of these lies all at once. What happens when it's not a massless pulley? Well, there's some problems. See, first of all, the fact that it's a non-massless pulley, or rather a pulley with mass, means that at the very least, there's going to be some energy lost, not lost, but somewhere other than in the blocks. As the pulley spins, it picks up a rotational kinetic energy, and that is energy that is no longer between the two blocks. Now we have a third piece where energy could be. What that also means is that to have gotten this spin in the first place, to have gotten this angular speed, there had to have been a torque on the pulley, and the only way that there could have been a torque on the pulley is if the tension in this rope right here did not match the tension in this rope right here. So, this is where we start to look at those good old days when we still had things like massless pulleys and tension was constant through the entire rope and all that good stuff. No, but that's all right. This is not actually anything super crazy. I know I'm adding some extra details here, but here's really what we have to do with this thing. Remember that the tension is the same between the rope, and the tension pulls anywhere the rope is connected. So what we can do, my hint for you here, is that this spot right here, this spot right here, these are the two spots where the rope is connected to the pulley. What's going on up top over here? Who cares? I don't care about that. That's not what's important for pulling these things. I'm much more interested in the tension at these two specific spots. Split this up first, of course, do this as you have been doing, right? Let's just get a sense of what this problem looks like in the old way of doing problems. Then I'm going to make a recommendation. Go ahead and call this side of the rope tension 1. Go ahead and call this side of the rope tension 2. And that will make this significantly easier to solve. But I'm going to mess with you even more here. Are you ready for this? There's friction acting on the axle. So, I know I'm being nasty here, but that's all right. I know you guys can handle this stuff. Break it apart piece by piece. And let's take the next 6 or 7 minutes to work on this one, and let's see what we've got. All right, so let's go ahead and start taking a look here. Let's go ahead and start by stealing this picture, though, because this is going to be a pretty important deal. So, but I am going to want to draw individual pictures for this thing. I don't necessarily want to just kind of stick with this the entire time. But let's go ahead and start with the easier side of things, right? The perhaps a little bit less realistic side of things. And let me go ahead and split it off kind of like, let's do a section here. Let's do it in blue to say, hey, this is old stuff that we have seen before. If we were in a case like that, we are looking for how long does it take for block 1 to hit the bottom. Here's what I would do. I would draw the free body diagram of each block. Right? I could use a conservation of energy. That could work. That's one way to do it, but that's got, I don't know, some extra steps. And a big part of the reason that I want to do it this way is because, largely speaking, what I'm focused on here is that the second method, as we look at this thing, that was not very good. This method right here using kinematics is going to look a little bit more similar to what I'm going to need to do down with the real problem. So let's go ahead and do this. Let's go ahead and label these things. And what I'm going to do with this as well is I'm going to go ahead and label the direction of all the forces, first of all, right? Of course, I'm going to have force of gravity 1. So let's call that, we'll just call it M1G. Going that way, tension pulling up. The direction of the acceleration, this is the heavier block. We expect the acceleration of this block to be going downwards like that. Block 2, tension pulls upwards. M2 times G pulls downwards, acceleration goes up. I want the time. I know the distance that needs to be covered is h. If I can find this acceleration, then time should be right after that. So let's start there. Let me go ahead and draw out each force equation for these things. So I would say for block 1, acceleration goes downwards. Let's go ahead and call our y direction like this. Acceleration goes downwards, negative m1 times a. T is positive, m1g, negative. Block 2, m2a, positive value because it points up. Tension is also positive, m2g. Let me go ahead and subtract one from the other. So let me go ahead and subtract. I'll subtract the top one. So let me swap all of these to pluses, this to a minus, and then stack these two together. Here's what that's going to look like. M1 plus M2 A is equal, the minus tensions are going to cancel each other out, M1G minus M2G, acceleration then should be something M1 minus M2 divided by M1 plus M2 G. If you want to, I don't even have that number written down. What we can do with this acceleration right here, what do we do? The last thing that we need, how does position relate to acceleration with time? Of course, we have our number one kinematics equation, the really, really big one. That is to say, if we wanted to fall a distance, oh, I found the quantity for my acceleration, didn't I? This is a positive value because that's how I've defined all of these things going down. Technically speaking, I know acceleration goes down, but this right here, what I've just found, is a positive number. Keep in mind that I have called it going down like this, so just keep track of that. I could say from here, h 1/2 at squared. Solve out for time. Time 2h over a square root 0.782 seconds. That's what we've got for that one. Now, let's look at the spicy version of this. I've got 3 different pieces that I'm going to need to look at here. three separate pieces. And one of the ways that we could try to consider this is energy, but I run into a little bit of an issue with that one because, well, to be honest, we haven't really described torque when it plays into friction and work and stuff like that. So we've got that difficult thing lined up with us. We haven't talked about that too much yet. But that's all right. If we look at this thing, we can just take this thing with acceleration instead. That works out perfectly well. This problem's not too spicy. It'll be all right. Let's go ahead and see what this thing looks like. So here's what I've got. My three pieces. I've got the actual pulley itself, something that looks like this. So I'm going to have, kind of in order here, here's the three different forces that I see, or rather, the three different torques. I'm going to have tension 1, I'm going to have tension 2, and then, let's go ahead and label those first. Tension 1 goes like this. Tension 2 goes like this. Which direction is this thing going to want to turn? What direction should the pulley actually turn? What do we know? Do we know things? Counterclockwise. I would agree with that, because block 1 should be falling down. It should be turning this way. That means friction hates that. Friction is going to apply a torque. Let me go ahead and do what I do best, make that a dotted line to say not a torque. That is an angular speed or an angular velocity. That means there should be a torque from friction. Let's call it torque friction, lowercase f. Not a specific force, that's just like the axle on itself, other stuff like that. We don't have that as a force, we have that as a torque acting on the pulley. Okay. So, does the pulley have acceleration? What do we think? Yeah, I'd agree. If it starts at rest and then I release it and the pulley is spinning to let the other block down, I would probably argue, well, yeah, it started at 0, it ended at not 0, it has an acceleration. So I'm going to say not only is omega here, but so too is alpha. Perfect. Now, that's my picture setup for now. Before I write down any equations, let me go ahead and draw out the rest of my pictures. I will have block 1. We'll go ahead and draw these things all together, right? One big happy family of kinematics. T1 pulls up. M1G pulls down. Acceleration goes like this. Go ahead and label that in just a second here. Block 2. 1, 2. Just to make sure we're keeping track of those. I would expect a tension pulls me directly up. M2G pulls directly down. Acceleration. That way. T2. M2G. Okay. Now, here is where we're going to have to start writing down some equations. And here's where it's going to get a little bit funky at first. Let me actually go ahead and start out with the pulley. So I know that there is an acceleration acting on this thing, which means that the net torque is actually not going to be 0. It is not an equilibrium situation. We definitely do have an acceleration. Newton's second law of rotational motion would say, all right, well then torque net would be equal to I times alpha, mass times acceleration, or their equivalents, would be equal to T1R is trying to pull me counterclockwise. That is a positive quantity. And to boot, the radius goes out like this, so this is a right angle. So sine of 90 is just 1. T1R. Tension 2 does the exact same thing, but in the opposite direction. So this is a minus T2R. Finally, we have friction, which just has some sort of quantity. They give us what that value actually is, so that's going to be torque friction. Okay. We need to do the exact same thing now for each of our boxes. So let me start there. Let me go ahead and say, all right, well then for box 1, M1A, much in the same way as right here, should be equal to IC, or rather, this should be a negative, right, because it's pointing downwards. this is going to be T1 minus M1G. Then I'd look at block 2. So positive M2A is equal to T2 minus M2G. So here's what I've got now. None of these things are time, but we're much in the same way that if we can find the acceleration, we're done. Right? Acceleration, that's the biggest thing to find at this point, because once we find acceleration, we can just plug it into the exact same equation that we saw last time, and we're set with it. So acceleration is really what we're after here. And before I highlight things, let me do one last thing here. Let me go ahead and take what I've got going on here with my torque equation, and let's mess around with it just a little bit. Let's change it up just ever so slightly. Let me first move this thing up just a little bit so I've got a little bit more space right under it. So a pulley is nothing but a big disc. That means that the moment of inertia of this pulley should be I is equal to 1/2 m r squared. So that's one thing. We've got that moment of inertia now. How does alpha relate to A? How does V relate to omega? How does theta relate to X? All of these things, remember, that one-for-one transformation right there, all of these things that we have seen so far, this big slide, all the things that we've got on this one. And we don't even have it on here. Why didn't I write that in somewhere? Remember that we can always convert from one to the other, just multiply by r. That is to say, the last thing that I guess we should add on this thing is that change of x, or x, would be equal to theta times r. V would be equal to omega times r. A is equal to alpha times r. So let's do that. And one of the things that I just noticed here is that I've already used lowercase r. Let me stick with lowercase r just for some consistency here. That is, alpha should be equal to A divided by r. So here's what I'm going to get. I alpha turns into 1/2 m r squared times A divided by r. And then all of this stuff does not change. This stays kind of right where it's at already. Let me actually do one more thing with that one. I've got one more step that I do want to add here, so let me move all these things down. We're almost ready to work with this thing, but there's one more simplification step I can do for this thing. So I'm going to see one of these r's cancels out. Right on the left-hand side here, squared crosses out with that one down there. Then let me divide everything by r, just for the fun of it, right? Why not? Because I'm having a good time with it. If I divide everything by r, then what I'm going to be left with here, so this to this to this, is going to be a 1/2 m a, very much like the others, is equal to T1 minus T2 minus friction divided by the radius. Now I've got a group of 3 equations right here that all look pretty similar. And let's look at the things that we know and the things that we don't know. We're really after A. We would love to have A, please. Right? That's our answer. If we can find A, we've got our answer. What things don't we know as well? Well, we don't know T1. And we also don't know T2. But that's all right, because at this point, we're done with the physics. We have done the physics at this point. We have replaced everything we need to replace. Now we have a system of equations, and it's time for algebra to take over. I'm trying to see if there's a clean way to do this one. And what I'm thinking here, it might just be easiest. My top equation right there has T1 and T2. My 2 other equations have T1 and A, T2 and A. How's about, let me take each of these equations. So let's take these 2 things. And let's turn those into T1 is equal to M1G minus M1A. T2 is equal to M2G plus M2A. And let's go ahead and plug in both of those to my top equation. So here's what I'm going to come out with then. I'm going to end up here with 1/2 capital M A, the mass of the pulley, M, is equal T1 T2 minus T2. And then here's friction just kind of floating off by itself. I know it's been a nasty ride to get here, but A, that is the only unknown left. We're here. We have done it. We're at the end of the problem, or just about. The worst of it is over, though. Let's move the A's to the other side. That ends up with something else like this. 1/2 capital M plus M1 plus M2. All of that stuff had an A in it. Is equal to what's left on the other side. M1G minus M2G minus tau F divided by R. Then divide by that factor right there. When we do that, and I don't know if I even want to write that out, I'm just dividing out by A. I am finding that A should be equal to something like 1.61 meters per second squared. We go back to our same equation from before. We say T equal square root 2h over A. I'm just going to rob that thing directly from our solution here in blue. Square root 2h over A. Plug in our new value for A, and what we should find is, now that it does take a little bit of a longer time, 1.114 seconds. So, if we weren't having fun before, I'm sure we are by now. But I did want to highlight this because look at the very end here. We kind of see something really similar to what we had seen from before, right? It's like, all right, well, I've got like an M1 minus M2. I've got an M1 minus an M2. Now I've just got friction kind of mucking things up as well. And yes, friction was given to us. That was one of our given variables here. But the other difference that I see in this one is not only is this extra little friction term added, but so too was essentially, here's the term from the pulley. The pulley also has to turn, and if the pulley also has to turn, then, well, it's going to have some factor in this. Oh, no need to be scared. You'll be masters at this stuff. I promise. You know these concepts. I promise you do. I know it seems like there's a lot of pieces in here, but you just need to approach it as you have been approaching these things before. If you take these things apart conceptually, then extra terms are only extra things to write down. Nothing more than that. I promise. It's the better way to look at things. Just take it apart piece by piece. You know how all these things should be. You know that things move, have things that are moving them. You can write down how those things are moving them. You've seen all these pieces. If it's just extra stuff to write down, it's a little bit more work in the algebra, but I believe in you guys. So, that's all I've got for today. So problems, send you guys off to the races now to work on some of these things yourselves. Of course, as before, I mentioned this before, please don't hesitate to reach out to me. I'm always happy to help with things, even if I can't respond immediately or anything else. In the case that I don't respond immediately, give me a couple hours. If I haven't responded then, just send me a gentle reminder email. Sometimes I get caught up in a lot of different things going on at once, and I let an email or two slip by. But please do not hesitate to reach out if you need help or anything else like that. And I'll see everyone again next time.